Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at numerical computation and, in particular, integration by the trapezoid rule. You've seen in calculus that the definite integral can be interpreted as the area under a curve. And if we evaluate this, we can do the antiderivative of f of x, evaluate it at b and evaluate it at a, and subtract those, and that will give us the exact area underneath this function. That's great unless, sometimes we get a function that can't be integrated. Or, in a practical sense, often we end up with things where we have experimental data that I need to integrate. And so in those sorts of cases, calculus isn't exactly the tool we need. We need to use those methods that we developed to define the integral. Do you remember doing like left endpoint rule and right endpoint rule and shrinking those down and getting a Riemann sum? Or maybe you did the trapezoid rule or the Simpson's rule in your calculus classes. We're going to be revisiting trapezoid rule and Simpson's rule in these lessons. So the trapezoid rule, the idea is that you look at a chunk of function and find delta x as the width between the two variable values of x. And then the height of that, the area is going to be the average height. So averaging the height at A and the height at B, the average of those times the width gives me the area. And I can improve upon this by breaking this into more and more little chunks of width delta x, where delta x is b minus a over n, the number of subintervals. And if I do that and I add them together, I can collapse it down to this form here, where the integral is delta x over 2 times the function at the left endpoint, a, plus the function at the right endpoint, b, plus 2 times the sum of all of the functions in between at every one of my delta x points. An algorithm that will do that is shown here. So I can choose how many subintervals I want, and I'm going to then use my limits of integration a and b to calculate delta x. So delta x is b minus a over n, the number of subintervals. I'll calculate the function at a, calculate the function at b, and then I'll calculate the function at every point in between. So a plus delta x, a plus 2 delta x, a plus 3 delta x, all the way up until a plus n minus 1 times delta x. This sum I will multiply by 2. I'll add it to these two values, multiply by delta x and divide by 2. That will get me a good, reasonable estimate of my integral. So let's look at an example. We're going to integrate x squared e to the x squared dx from 0 to 1. And this is something that I just offhand don't know how to integrate. So we're going to open our Excel, and I have set it up so that I have the limits of integration set up here, and I'm going to do Visual Basic for the rest of this, and I'll have it put the answer in that cell right there. So what I need to start with is I'm going to insert a new module. Let's bring it up here. And I'm going to create a sub that I'm going to name Trapezoid. And I'm going to, I've started this so that I have the basics of the program started. I'm going to read the limits of integration from the spreadsheet in cells B1 and B2. I'm going to ask the user to enter the number of intervals in. And the reason I'm doing it that way is because I want to make this a little bit easier to try different values. And to me, that's just the quickest way. So that's just a convenience thing. And then I'm going to create a function. I'm going to name it example1 of x. So function and example1 will be equal to x squared times exponential of x squared. And I didn't really have to name a function. I could just type that in every time up in my sub. It just seems easier this way. And it gives me something that's going to be faster to edit when I want to use this same program for other functions. So now then, what the algorithm tells me I need to do is I need to calculate FA, which is my example1 evaluated at A. And I need to calculate FB, which is example1 evaluated at B. And then I'm going to start my sum. And it's FA plus FB. That's the first two pieces. Now I want to add in all the rest of the pieces. So I'll put in a loop. The rule says I'm going to start at 1 and end at n minus 1. I'm not going to have to make decisions about how many terms or anything like that. Am I close enough? I also know that I'm going to need a next, so I'm going to go ahead and type that in, and I'm going to indent to make sure that everything in this next part is truly between the for and the next. I don't want anything to kind of overlap that, and nesting is going to be important, and we'll be talking a bit more about that in a future lesson. So in this particular case, what I want to do is I want to add to my current sum the next function. Now all of these other pieces are going to be doubled. So 2 times example1 evaluated at A plus I times delta x. Okay, so that's going to get me my function. And then I need to create an answer. So the integral is equal to, all right, the formula said I'm going to take this sum of all of these things here. I'm going to multiply by delta x, and I'm going to divide by 2. Now I need to output that. So range B3, select, and active cell value is equal to the integral. All right, let's try running this. How many intervals? Well, let's choose a small number, 5. Okay, got me 0.663. And what we remember from calculus is as we let n go to infinity, it's going to get to be a better and better answer. So let me run this again. This time let me go to 50. 0.628. I can run this again. We'll do 500. 0.6278. Okay, so it's getting closer. I don't know what I just hit there. All right, let me run this again. Let's say I did 500 last time. Let's do 5,000. Okay, so it seems to not be making much change. And I can continue increasing this. Now, because I've set n as being an integer, I am capped at a value, it's like 28,800 something. Okay. So I could do it for as much as, say, 25,000. Okay, and I'm not seeing any change, so there's not really any point in this next one. But integer will not go if I wanted to do 50,000. It will give me an overflow error. Okay, so be aware of that. I could change this to long. Okay. that is a way to get to longer integers, but really there's no need. I wasn't seeing any change. So this is our basic trapezoid rule. I want to very quickly look at another example though, because what about those cases where we have experimental data? So I am going to copy that data over here and show you how that can be done. Okay, so the way I'm going to do this, sometimes if you want to do something and you know how to make Excel do it, the easiest thing to do is record a macro, which is actually going to create code for you. So I'm going to name this, okay, macro 2 is what it wants to call it. Control J. It's got to be something that is not a normal shortcut. And I don't really, normally I would say write some code in there. I want to start at my top of my column. Actually, I want to start over here and equals count. I want to start at the top of my column and I want to go down. I don't know, how many data points do you think you would ever possibly need? All right, and that's going to give me that. So I'm going to now stop recording and let's go look at what it created. So if I come back to my Visual Basic, module 2 is what it created. All right, so what it did is it went to cell C5, it selected it, and then in that cell it wrote this. I'm going to borrow that and come over here to module 1. All right, so I first need sheets. Sheet 1, select. Range C5, select. Active cell formula is that. And then I'm going to say that n equals active cell value minus 1. Remember that if I count the number of data points, that has also the endpoint, so I need to subtract 1 to get what n is equal to. All right, so now I have n in my program. I'm going to start my sum with sum equals 0. I am going to now come to my top, and I said that that was A7. And what I'm going to do is I'm going to, actually I need the function. I don't care about what the x is. Actually I do need that. Okay, so A is equal to active cell value. And what I'm going to do is I'm going to set up the formula so that I start here and I'm going to go to each point and I'm going to hop through the cells. So I'm going to pause this and write that code. All right, so I have typed in some code. Pause this and take time to read this, but this is the part I borrowed from my macro. N is that value minus 1. And then I moved back over to the start of my data and I went from here, I hopped over to here, so I read A, I hopped over here and read f of A, and then I just read f of I for each one of these values by simply hopping down one cell every time. So in my loop, I'm going down one row, staying in the same column, reading the f sub I value, and then adding double that to my sum. Then I came down and did f sub B and added 1 times that to my sum. I now needed to know what B was to know what delta X was equal to. So I have it, I'm down here at this cell. I come back over here to the 0.6 and read that one. That's B. That calculates delta x, which can calculate my integral, and I come up and enter my answer. So let's look at this. I run it, and yeah, it gets me an answer that looks like it's about right. Okay? So that's a way that we can do this so that it will automatically find the number of data points available so that it can calculate the number of intervals. So this concludes this lesson. We're going to, in the next video lesson, look at Simpson's rule. Thank you very much for your time.